IPA. So we're going to talk about mine backfills today here, but it's not going to be my traditional mine backfill talk because I want to spend some time talking about how the global perspective on waste disposal is influencing the backfill business. So we'll talk about a lot about stakeholder expectations and stakeholder demands and how they are creating changes in the global practices for backfilling. So I'm going to kind of run through a bit of a history of mine backfilling to kind of get you to where the backfill business is today. We're going to talk a lot about paste fill because nowadays that is definitely the backfill of choice. And we'll talk about the science of paste filling and how that's leading to some of the global practices now. And then, like I said, we're going to spend some time looking at some recent events and how that's kind of changed the industry. So really the backfill business, and certainly here in Peru, goes back to about the 1950s and through to about the 1970s. Hydraulic fills dominated in the backfill business. And by the 1980s, there were a lot of demands made on backfills where there was created a demand to kind of change the backfill business and look at better filling methods. And this really led to the research that went into the adoption of paste fills in the 1990s. And once we got into the paste filling business, that started putting a lot of demands on the equipment. So we saw a rapid evolution in the types of equipment that were used in backfill. And then really since about the early 2000s, we now see the global acceptance of paste for backfilling. So we talk about backfill in terms of the mining cycle. Everybody's familiar with the mining cycle where we drill, we blast, we muck out the material, and then we put some sort of a fill in there in order to complete the cycle and allow us to go in for the next round of drilling. Now in that cycle there's not a lot of flexibility with time because the drilling, the blasting and the mucking is an operation that takes a period of time that doesn't have a lot of flexibility in terms of saving time. But when it comes to the backfill typically involves a period of rest while we wait for the backfill to cure, while you're waiting for the cement to cure. And that cycle can take anywhere from a few days to a few weeks. And at that stage, the mine is basically unproductive in terms of that stope. You have to go and mine other stopes. So if there was a way of speeding up the fill cycle, it would allow the mine to increase its productivity and we can increase the throughput. And I think that's one of the big advantages that we see that's come now with this kind of transition going from the hydraulic fills to paste fills is being able to shorten up the cycle time because we don't require the curing times with the paste fills, and this leads to higher productivities in the mine. So in terms of the backfill that's in use today, obviously here in Peru, you're still dominantly based on hydraulic fills. There are a lot of very large hydraulic fill operations here in Peru. You can see my pictures there from the Centramine days up at Cubriza and Cerro de Pasco. And slowly the industry is converting hydraulic fill operations into paste fills. Here in Peru you have about a dozen paste fill operations. But there's still a lot of mines that rely on rock fills, and the reason is because the rock fill is able to achieve strengths that no other type of fill can achieve. So when you have a very high stress situation, particularly if you're doing mining undercuts, or if you're in a very high stress ground, we still see a lot of operations that rely on rock fills. But you know, the cemented rock fill really is worldwide is a dying business because there's probably been more cemented rock fill operations that have converted over to paste than there has been with hydraulic fill operations. So if we look at the uses of backfill in terms of the industry drivers, you know, in its simplest form, we use backfill just to fill the voids. So basically, we're returning mine waste underground, and in a lot of cases, this is a complementary part of the mining cycle because we're providing a working floor in order to do the next lift of mining. Obviously, the benefits to using the backfill as a void filler, and these are benefits that you would easily see improve, you know, being able to reduce the surface disturbance and returning more of the materials underground, having lower water treatment costs for treating water from tailings basins and the like, easier project permitting, which in a lot of jurisdictions now is really becoming quite an important factor, and of course reducing the closure costs and the liabilities long terms at the end of the mine operation. And there are quite a few operations that improve that look at doing a sulfide separation at the end of the flotation in order to selectively place high sulfur tailings underground and put the lower sulfide tailings on the surface, again in order to deal with the environmental impacts. And so when we're using the backfill as a void filler, generally there's no load. So a lot of times we can get away with putting that material in with no cement at all. And certainly there are a lot of hydraulic fill operations here in Peru that would use no cement. They're providing a working floor. But the real benefit of backfill, of course, comes from being able to use it for increasing the ore recovery. So basically, the backfill allows us to mine ore bodies that wouldn't be economically mineable otherwise, and we're able to get much higher extraction ratios, send a lot more of the material to the mill by providing ground support during the mining. And typically this is done in a kind of a primary secondary stoping sequence where you have large open stopes, long hole stopes, or a sub-level. And in this case we have to add cement because the material is not self-supporting without cement. So cement consumption becomes an issue then. In the secondary stopes, in a lot of cases you can get away with putting in uncemented fill, and in fact it's quite popular to put uncemented rock fill in secondaries, but cemented tailings in the primaries. But generally, unless we're a very large mine, you know, we're looking at fairly moderate strength, something in the order of about a half an MPa compressive strength. And this type of a method, of course, is suitable for any type of fill, whether it be a rock fill, a hydraulic fill, or a paste fill. Because these fills are generally not designed to carry a load other than providing pillar support and being self-supporting. So if you're in a situation where you have a hanging wall putting a load on the backfill, that really goes to the next level of fills, which I'm going to talk about here, which is mining in a high stress ground where you have stress transfer to the backfill. So in the case of the high stress ground, traditionally mines have used cemented rock fill because the cemented rock fill gives you a very stiff backfill at fairly reasonable cement contents, you know, something in the order of 5% cement. But with the advent of paste fills, a lot of mines are finding that the paste actually provides more benefit than the rock fill. And that's because of the yield strains that are imposed in the fill. And the chart that's in the bottom there gives you an excellent example of going from about a 250 MPa paste fill, where you have a very high yield to strain to failure, well over 3% strain. And then as you progressively add more cement, you increase the peak. So you see the peaks rising with the different colors until you get up to the red where you have a 4 MPa fill. And so now you have a very stiff paste fill. And now you're looking at about a 0.5% yield strain to failure, but at a much higher compressive strain. So it's the ability of the paste fills to be able to absorb these strains that makes it very suitable for use in high stress ground. But I will caution you, the design process is very complicated. It's not something that you can do on the back of an envelope or in an Excel chart. It really needs doing proper numerical modeling. So if I kind of jump backwards here in terms of the history of backfilling. So in Mexico, for example, we see lots of mines that show evidence of mine backfills that go back to the days of the Spanish conquest. And I'm sure you probably have mines here in Peru that have 100 years of operating history with backfills. And in those days, of course, they didn't understand the science or anything, and there really was no science behind it. The only reason they did it was to allow them to provide a working floor in order to access the ore. But in the 1950s, we started to see hydraulic fills becoming more and more common because of the comminution techniques that generated coarse tailings, and those coarse tailings could then be slurried and returned back into the mine as a slurry, which was very inexpensive. And then with the introduction of Portland cement in the 1960s, we were then able to start using cemented hydraulic fills, which allowed the recovery of pillars, as we just seen. However, the introduction of these cemented hydraulic fills did not come without problems, and one of the biggest problems being the very high cost of the cement, because the cement consumption was high. Any of you that have worked with backfills know that your cement cost can easily be 70% of the operating cost of your backfill. So it makes up a very high proportion of the cost. And the other problem, of course, is that when you're pumping a hydraulic fill, you end up with massive volumes of decant water, which is generally very dirty. It carries a lot of the slimes get carried out with the decant water. And if you're in a region like South Africa, where they have mines that are kilometers deep, pumping all that water down deep into the mine is a major cost, because they've got to get all that water back out again. And then to make it worse, the metallurgists started playing with the grinds, and they made the grinds finer and finer for the flotation circuits. So we find that we get less and less sand, and we're in a position where we have to accept more and more slimes in the hydraulic fill. So this really was the impetus for doing the research into the early days of paste backfills. And it really was in Canada, through INCO and in South Africa, where most of that effort was expended, and they were looking for ways to reduce the water that was being pumped down into the mine. That was the main focus back in those days. So one of the early solutions that came out was this so-called tail spinner, which is basically a centrifuge. And the tail spinner basically produces a filter cake, and that filter cake was at a solid content that it could be pumped, or it could be pneumatically stowed in a stove, and you didn't have all that return water coming out then. And in 1978, the first tail spinner was granted a patent, and it was put into use in the Wits Basin in South Africa. And ironically, the first paste systems in Canada were actually based on the tail spinner technology, going all the way back to about 1983 at the Dome mine and at South Porcupine in Canada, where they had what we would call the very early beginnings of a paste system. The big limitation with this system, of course, was the throughput. You could only get 15 tons an hour out of this piece of equipment, so it didn't lend itself very well to the types of mines that we do today. So with that work, we saw kind of the beginnings of paste backfill in the early 1980s. And back in those days, you know, I don't even think the word rheology was even known. And certainly people didn't understand the rheology. They didn't appreciate how rheology impacted the behavior of these materials. And it wasn't until the late 1980s when a South African by the name of Merkirk actually started doing rheology experiments on thickened tailings, looking at transport of thickened tailings. And he produced the first rheograms for thickened tailings and what we would call paste. And he was the first to publish a paper showing that these materials act as a non-Newtonian fluid, and that their properties are governed by the yield stresses and by the viscosity. So that work was going on in South Africa, and at the same time we had some early paste systems going in the US, Lucky Friday, for example. But those systems were basically based on trial and error. There was no science involved in those systems, and they made a lot of mistakes and there were a lot of failures. So it wasn't until about the early 1990s that the mining companies got involved and started spending money on researching the properties of paste. So what came out of that was that we began to realize that there was a science behind the rheology of paste. And if I start with the very basic definition, because it's amazing how many people don't understand the difference between a slurry, a thickened tailings, and a paste. And the way that us backfill engineers define it is that a slurry is a suspension of solids. Thickened tailings is equivalent to taking that suspension and pouring it into a beaker and letting all the solids settle, and then you drain the water off, and that material that's left in the bottom of the beaker would be called a thickened tailings. But when you go to paste, you're actually doing, you know, some sort of mechanical action in order to remove more water, and at this point you start to get point-to-point contact between the particles in the paste, and that's why it behaves differently than a thickened tailings. So everybody knows the kind of the industry definition of paste as being a non-segregating, non-settling material, and that definition still holds, but those of us that are in the backfill business would prefer that people get to understand the science, because our definitions are all based on science now as opposed to the industry rules of thumb. So the early science of paste really came out of concrete technology, and I think it was in particular the researchers in Canada looked at the way that concrete behaves, and they used that knowledge in order to drive the research into paste. And so one of the rules of thumb that you see out there for paste is that it has to have 15% passing 20 microns. Well, the recipe for concrete is 1 part cement, 2 parts sand, and 3 parts gravel. So the cement is about 1/6 or 15% of the fines, and that's where the 15% rule came from. And of course, all of our paste work is all the rheology work at most mines even today is based, primarily on slump cone measurements, which is a method that came out of the concrete industry. So what they realize, of course, is that when you pump paste, you get this plug flow phenomena where you have shearing on the walls, and then the material in the core of the pipe acts as a plug. And that plug flow, the resistance of that plug flow is driven by the fines that are in the paste, and it's driven by the water content, basically the yield stress in the paste. So the entire paste business is summarized on that one slide right there. So basically what we're showing here is the definitions going from, so what I should point out, you got percent solids along the x-axis and the yield stress along the y-axis. So a typical paste rheogram. So here we transition from a slurry to a thickened tailings to a paste and then eventually to a filter cake. The transition from the slurry to the thickened tailings takes place at about a 20 Pascal yield stress, and the transition from a thickened slurry to a paste takes place at about a 100 Pascal yield stress, and then by the time you get up to about 800 Pascal yield stress, now you're talking about filter cake. Now these are not solid black lines, they're very thick gray lines. Depending on the material and the mineralogy and the chemistry of your tailings, you know, obviously these points move around. But what this slide also shows you then is the various methods of producing these materials. So you go from, you know, a segregating to a non-segregating material using unfiltered, moving into a conventional thickener, moving into a high-density thickener, and what we would call a paste thickener. And in terms of the thickening continuum, what the curve shows is that as you go up the curve, you have increasing residence time in the thickener, and that means then that the thickener has to have an increasing volume. So just from a visual aspect then, that thickening continuum, you go from the slurry, which is just based on conventional thickening, and it might be at, you know, 40 to 50% solids. You get into the high density slurry, where now you're looking at something in the order of 60 to 65% slurry solids using a high rate thickener. Then you get into what we call the high slump paste, where now you have to start looking at a larger thickener, and typically nowadays it's a deep cone or a deep bed. Now you're looking at something that's north of 70% solids, and then you get up into the low slump paste, something in the order of a 7-inch slump paste. Now you have to go to filtration in order to get the solids contents, because you can't produce the material from a thickener, because you're talking about solids contents that are in excess of 75%. This slide, I apologize, is a commercial slide produced by Westech, just showing their particular line of thickeners, but I just wanted to show you how, as you go up that yield stress curve, it's going to drive the decision as to what kind of a thickener you're going to use. So at the low end, you're using a conventional thickener, and in order to produce the very high solids content, very high yield stress materials, you're going to have to look at a deep cone or a deep bed thickener. So I just want to spend a few minutes kind of looking at all the different types of equipment that would be in a backfill plant, and show you how the industry, you know, has put the pressure on the manufacturers to deliver products that are more suited to what the backfill business needs. One of the most fundamental pieces of equipment, of course, is the hydrocyclone, which even in your hydraulic fill plants would see wide pres used. And this equipment's been around for well over 100 years, 125 years. First patented in the late 1800s, and they were built out of wood. And they served the coal industry at that time by taking out all the contaminants out of the coal. In the late 1940s, early 1950s, these units were commercialized for metal mining and dealing with metal tailings by the Door Company. And then, of course, in 1955, Krebs was formed, and Krebs even today is still one of the larger manufacturers of hydrocyclones. But the basic concept behind the operation of a hydrocyclone has not changed in that time at all. What's changed is the materials that they're built out of, and the control technology in order to control the stream of material that reports to the underflow and the overflow. But the actual concept is virtually the same. Of course, the thickener plays a very, very important role in the business. And again, these units are over 100 years old, dating back to the early 1900s, where the first designs were produced using rakes in a circular tank. And then in the 1990s, Alcoa started looking at treating bauxite residues for alumina plants, and they actually produced thickeners, paste thickeners, or at least thickeners that could produce a paste for bauxite residues, because this material is extremely hard to dewater. And in the late 1990s, it was realized that that technology was very well adaptable to the mineral industry, and so we started seeing metal mines getting into that. So the technology was licensed to Alcan, and they sold those thickeners through the IMCO company to the non-alumina industries. The first units went in 1998. And even today, the modern paste thickeners, still rely on that same technology, although there's been a lot of evolution in those thickeners, which I'll talk about in a few minutes here. And really the paste industry put a lot of pressure on the manufacturers to come up with improvements. So what we see now is that, the newer thickeners have much better rake designs, and they can handle much higher torques. There's been a lot of engineering that's gone into the shape of the beds, looking at the angles of the beds and the volume in the bed. One of the big improvements has been putting in the dewatering pickets, because the problem with the paste is you pour the material in the top, and then you're supposed to squeeze the water out so that you get the thickened tin that's come out the bottom. But that flow path to get the water out is a very long flow path. So by putting in these dewatering pickets, they shorten the flow path, which speeds up the thickening process. There's been a lot of work done on flocculant chemistry, and today there's well over 300 of these deep cone units that are in operation, both for surface paste disposal and for underground paste disposal, at over 100 mine sites. And for a lot of mines, it's the core of the plant is a deep cone thickener. There is a difference between producing a paste for surface disposal versus producing a paste for underground that's illustrated on this particular slide. And that is that thickeners do not produce a uniform underflow. It cycles over time. And if you look at the performance of any thickener, particularly a tailings thickener, you're going to see this same curve. And the reason you get this is because of changes in the mineralogy of the material going in, changes in the particle size, changes in the clay content. If you have any dissolved salts or other dissolved minerals, it can have a huge influence on the thickening process. And of course, as you're moving through the mine, you're changing sulfide content, you're changing oxidation, all kinds of changes in the ore mineralogy over time that will produce this cyclical behavior. And in the bottom slide, you see a change in the ore. So you see that it's cycling up and down, and then all of a sudden you got into a material that maybe had more sulfides in it with higher SQ material, and all of a sudden you see that the torque on the rake increases dramatically in a very short period of time, and you'll see this process going on over the process. So for the backfill business, we don't like this, because we tend to have very tight operating parameters that we use for the paste per mine backfills. We want to control the percent solids to within about 0.5%, and so we don't like these fluctuations. So most paste plants for underground disposal would still have a filter cake component that gets added into it in order to level this out, in order to kind of mask that behavior. But still, you can thicken the tailings cheaply and quickly by doing a kind of a pre-treat with the deep cone. Of course, the other thing that happens with a deep cone that a lot of people don't appreciate is that after the material comes out the underflow, it then goes through a pump. And you get a pretty significant shear thinning when it goes through that pump. So you can see the blue dots is the yield stress of the paste before it went into the pump, and then the red dots are the shear stress, the yield stress of the material after it goes through the pump. So in this particular, this is real live data. It goes from, you know, something in the order of 120 Pascal yield stress before the pump down to about 40 to 60 Pascal. So it's halving the yield stress by going through that pump because of the shear thinning. So just some photos to show you how these rakes have evolved over time. So up in the top photos there, you see the old original IMCO designs, which really had nothing in the way of pickets on the rakes. It was just a giant rake with a big motor on it. And then on the bottom you see the modern rake designs, which have these pickets to speed up the movement of water in the thickener, and also to help to stir the tank. So the last aspect of the plant then, of course, is the filtration. And again, not surprising, the filtration technology has been around for a very long time, well over 100 years. And as in the hydrocyclone, there really hasn't been any significant technology improvements in the filtration for tailings. But what has changed is the cost. What used to be, I can remember when I first started out this business, a Larox filter press was something in the order of $2.5 million, and it cost 75 cents a ton to operate it. Nowadays, these units sell for a fraction of that value, and they operate at much higher efficiencies, so they produce thickened tailings, filtered tailings at a much lower cost. So all of that is good for the industry. So there's a number of different varieties of filters that are available for thickening tailings. The ones that we generally rely on, probably 90% of paste plants would have disc filters, and the remainder would have the horizontal belt filters. The horizontal belt filters do have an advantage in that you have a longer retention time, and you can produce a thicker cake, and they have a much higher throughput, require less maintenance than the disc filters. But for some reason the reason people like disc filters is because they're compact. They take up a lot less space in the plant, whereas a belt filter takes up an immense amount of space and makes for a very large plant. So once we've made our paste, now we've got to get it into the mine. So I talked earlier about the work that Verkerk was doing in South Africa, trying to assimilate pumping of paste to the pumping of concrete, for example. Now, of course, you know, concrete's got aggregate in it, so it's not surprising that some of the very early paste systems had aggregate in them. And actually here in Peru, at Andachawa, you know, you have kind of an aggregate-based paste system. And so people were adding the aggregate because they were essentially trying to make concrete. And Verkerk was one of the first to notice the conundrum that if you add aggregate to thickened tailings to a paste, it actually lowers the resistance in the pipeline. So in these very early systems, a lot of them added the aggregate in order to lower the pressures in the pipeline because they weren't capable of pumping it otherwise. Even the Lucky Friday, the early startup of the Lucky Friday system in the US had aggregate in it. The very early Boliden systems in South Africa, at Gardenberg and the like, all had aggregate, and all the very early systems in South Africa all had aggregate. So, you know, what you find is that when you get into this laminar flow condition, as you increase the coarse fraction in the material, you start to increase the resistance at the pump. But when you get into the non-Newtonian range, so you go from the laminar range, which is a slurry, into the non-Newtonian where you get into the paste, then the opposite is true. You start, as the coarse fraction is added, the friction losses go down. So in 1992, when these early paste systems were going in, it was said that you could not pump paste. People didn't believe that you could pump paste, and of course, with the experiences they had at Lucky Friday, it's not surprising because they broke a lot of pipes trying to pump paste at Lucky Friday. But by 1994, somebody come up with a way to pump paste 1 kilometer, and by 1998, we were able to pump paste 3 kilometers. Nowadays, you know, the practical limit is probably in the 2 kilometer range, but there are lots of systems that pump paste 3 or 4 kilometers. And when you look at some of the soda ash systems and potash systems in Canada, for example, you know, they pump paste, you know, upwards of 5-6 kilometers, but these are very, very low yield stress paste. So like I said, you know, Lucky Friday, they learned a lot of valuable lessons about free-falling paste in boreholes and having abrupt bends, allowing air entry into the pipes and the like, and a lot of that goes into the way that we design the paste systems now. So 1970, there you see a Putzmeister concrete pump truck with a 100mm delivery line. And then by 1980, Putzmeister was supplying pumps to the Bad Grund mine in Germany, which a lot of people talk of as being the very first paste system that was installed in the world. Now, again, Bad Grund also had aggregate in their paste. Nowadays, of course, the pumps are a lot more sophisticated. I should say that the technology really hasn't changed, but what has changed is the control systems that operate these pumps so that they're able to operate at ranges that weren't feasible before, and of course they can handle much higher pressures than they could before because of the technology that's gone into the valves for delivering the paste to the pump. So on the left there you see a double-cylinder Putzmeister pump, and if you look on the pipeline on the right, you can see an air dampener that's that takes the cycles out of the pump when you get the compression cycles, which transmits a shock wave down the pipeline. That's a surge tank that removes those surges down the pipeline. And then on the right side you see a Wirth pump, which is a piston diaphragm pump. And these pumps are massive. I mean, you can see the size of the people standing in the room. I mean, that pump would fill this whole room and plus more. I mean, they're monstrous pumps. But they will pump, you know, 1,000 cubic meters an hour and at pressures of you know 200 MPa, 20 MPa. So the early adopters of paste, the first Golder Paste Tech plant that went in was 1998 at Cannington in Australia, and ironically this was the second paste installation that went to Australia. The first one that was done in the 1980s didn't work, and that plant was a failure. You see there the 1997, the Stillwater, which was the very first Alcan deep cone paste thickener that was installed under the Alcan licensing agreement in the US. You can see the bauxite residue plants in Jamaica. Averton was the very first Alcan, very first Alcoa one that was put in about 1996, I believe. And then you see Persian Parinjo Gold in Australia in 2000, which is an Odotech design. So all the big thickener manufacturers all make deep cone or deep bed thickeners, whichever you want to call them. They all have their own variety. So as it stands now, we have about 150 paste plants that are operating worldwide. At least a dozen of those plants are here in Peru, and the industry adds about 5 new plants a year. So the operation of these plants, obviously, the control technologies are a lot more sophisticated. You can see the Garson plant in 1994 on the left there, which was just a small, probably an amber monitor hooked up to an XT computer. and then a modern paste plant which has multiple screens and an HMI system. Everything is all regulated and controlled just like any normal metallurgical plant, a lot more sophisticated. And of course all these plants all now have fiber technology for being able to have cameras to have a live feed so you can actually view the paste going into the stove. And of course the actual quality control process has evolved over time. It's amazing how many mines still prefer to rely on the traditional ASTM slump cone, whereas other mines are adopting rheogram. So you can see the rheogram in the foreground on the left there, and in the background you can see a laser particle sizer, and so they do routine quality control. This slide was from a presentation I gave last year, and it kind of shows how the paste business has been adopted over the years. So you can see the two main symposia, the Mine Backfill Symposia, which is held, it's an international conference held every 3 years, and then the Paste Symposia, which is an annual conference. This coming year will be in Santiago. Last year it was in Australia. And you can see how many papers are published that make reference to paste. So, you know, prior to 1989, in the Mindful Conference, there was virtually no mention of paste. And then you can see how the number of paste papers has exploded over the years, you know, up to 2013. And the same is true for the Paste Symposia. We see that as time goes on, we see more and more papers coming in. It's just kind of a measure of how the paste backfill business is being accepted as a global standard now. So we've talked, you know, about the roles for backfill. You know, using it as a void filler, providing a working floor for overhand mining, and very importantly for providing us with resource extraction by being able to recover pillars and being able to recover broad disseminated ore bodies that might otherwise not be able to be recovered. And of course the backfill business brings with it improvements in the ground control, particularly in rock burst prone ground, by improving the safety in the mine, and then of course decreasing subsidence. And here in Peru, you know, you get some very specific benefits in terms of being able to return the mine waste underground and being able to mitigate surface environmental impacts by disposal of highly acidic tailings and highly toxic tailings. But it's unfortunate, you know, that as the industry marches on, we have events that change the whole industry. And this Mount Poly tailings incident in Canada, I know this is an open pit mine and it may not be particularly relevant to mine backfilling, but it is relevant to how it's going to drive the industry, and it's going to have an impact on mine backfilling, because it's going to help determine what the future of mine backfilling is going to be. So, you know, in this Mount Poly incident, you know, this was Imperial Metals is a Canadian company. They have 5 operating mines, about a $2 billion market cap company, and this Mount Poly is a copper gold mine in kind of north central British Columbia. They're mining about a 0.3 copper, 0.3 gold, fairly typical for a porphyry copper deposit. And so they had this incident in August last year where the tailings dam was breached and released 10 million cubic meters of water and about 4.5 million cubic meters of tailings slurry, and completely inundated the creek downstream and inundated Poly Lake, and the impacts were felt all the way down to Quesnel Lake. Fortunately, there was never any heavy metals recorded in any of the discharge water. It was rather ironic that all of the water quality tested returned drinking water, standard water, even after the incident. And so there was never a huge kind of environmental impact other than the disposal of the solids and of course the massive damage done in the same. But when you think about that incident in terms of the secondary value to a mine, you know, you can see a couple of newspaper articles there where, you know, initially Mount Poly said, well, it's going to cost, you know, something around $70 million to clean this up, and then a later article they figured it's going to cost upwards of $500 million to deal with all the impacts. So, you know, all of this figures into the equation of what kind of a backfill plant you're going to put in, because the downside to the paste systems now is that paste plants are getting to be very expensive. And I've been working on a couple of paste plants in recent years where we're looking at capital investments of over $100 million to put in a paste system. And a lot of mines will look at that and they think, well, we're not going to invest that money. It's just not worth it. We don't get any return on our dollar for that. But when we have incidents like this, it's almost like the hand gets forced at some point, because you have to consider the downstream impacts of these types of events. So the future really is going to come into having a consideration that links both the surface disposal to the underground disposal. So what happened after Mount Poly was that there was a huge outcry as to how is it that a reputable mining company in a very well-established jurisdiction with a very rigorous permitting and regulatory process, and they've got highly qualified mines inspectors and annual inspections and all that. Like, how could the thing fail? Like of course, the people that were against it immediately said, well, what that means is that it's impossible to build a tailings dam that will not fail, because if this one has failed, every tailings dam is going to fail. So there was an immediate backlash in Canada against the mining industry as a whole, but in particular against the disposal of surface tailings. And the next thing that happened, of course, was that the First Nations groups decided that they wanted to be part of the permitting process, and they wanted to have a say in all new mine permits. And then, of course, Alaska got very upset because the project was very close to Alaska. So what that means is that for the mine backfill business is that we've got to put the tailings back underground. There's going to be increasing pressure to put tailings back underground. And the future of the industry is going to be that the stakeholders will no longer allow the practices of the past, and they're going to want minimal surface disturbance with minimal impact, minimal disposal on the surface. The regulators are going to push to outlaw the wet tailings, and the mining companies are going to be forced to come up with technologies that meet these demands. And you're going to see a lot of pressure on the surface disposal that will have impacts on the underground disposal. So what's ironic about the Mount Poly incident was that they focused on dry stacking. When in reality, dry stacking, as I said, is not the solution for every mine. But they never made any mention of paste thickened tailings. And a couple of years ago, at the PACE conference in Australia, Andy Fourier from the Curtin University got up and said that out of 130 some odd thickened tailings facilities that have been built worldwide, there's never been a failure. And he even noted that the massive earthquake that happened a couple of years ago in Chile, there were over a dozen very large tailings facilities that received some fairly massive shaking, and none of them failed. And the reason that we don't have the failures in the thickened tailings facilities is because the void ratios are so much higher. And when you combine that with the evaporation processes, which cause kind of a self-consolidation of the material as it's being placed, you take the material down that critical state line to the point where it can't liquefy anymore. So again, I realize that this is not mine backfill, but the point of my discussion here is that we have to, I'm going to just skip that slide, we have to marry the surface solution with the underground solution. And paste thickened tailings is a perfect brother to paste disposal for underground. And more we're starting to see dry stacking being combined with paste. Milpo at Cerro Lindo, as all of you know, do dry stacking, and they also have two paste plants that operate there. And the reason is because we're using the same technology for the thickening and the filtration, and it's just a matter of this material goes this way, that material goes that way. What doesn't work for these facilities is if you have to separate the tailings. So for example, using dry stack with hydraulic fill is I'm sure some of you have come across this suggestion where we do hydraulic fill, but we're going to take the material that we can't put underground, we're going to take that material, we're going to dry stack it. Well, unfortunately it doesn't work, or at least if it does work, it's very expensive, because the problem is that you're trying to filter the fines, and filtration of fines is a very expensive and very tedious process. It requires a massive filtration plant, and it's very expensive to operate. So it's not a very clean solution, but if you go to the total tailings solution, the two solutions marry together. So I'm just going to very quickly run through just a couple of other best practices while I wrap up here. But you know, in Australia, there's a lot of focus now on farming of existing tailings for use in paste backfill. And so what they're doing there is they've got, you know, an operating history with tailings sitting on the surface. Fortunately there, the material is drying and desiccating in this pond, so it's already dewatered, and they're able to mine this material and basically feed it into an aggregate plant. And all it consists of is a shredder to break up all the lumps in the tailings and take all the organics out. You put it in a mixer, add water and cement, you've got paste, off it goes. And there you see 3 operating farm tailings plants that are in operation in Australia right now. Very simple plants. You can build these plants for under $10 million compared to, you know, $50 to $80 million for their equivalent if it was a full paste plant. Of course, a lot of the best practices for mine fills, when we talk about the safety aspects of mine fills, really come down to the barricades. Because in terms of failures in mine backfill systems, we have more failures that are related to barricades than any other type of incident. So when you talk about best practices for mine fills, there's a lot of focus on barricades. So the barricades obviously would apply to the hydraulic fills and the paste fills, where we have to contain a liquid for a period of time. But it's a very complicated design because the loading on the barricade is time dependent, and of course the material is changing properties over time because it's curing. As that cement cures, the material stiffens, and it's tying up the water that's in the backfill. So the selection of the barricade becomes very, very important. In the case of hydraulic fills, we're looking at a short-term solution, because once that material is drained, it basically becomes inert. And then in the long term, you know, you're looking at something where you're providing the long-term drainage in order to make sure that you don't have any hydrostatic pressure on the barricade. There's a lot of different choices for barricades, and some of these pictures are actually from here in Peru. But when it comes to paste, for example, people seem to prefer shotcrete or the waste rock barriers. These cable fences, that's actually in Brazil, at Anglo Gold in Brazil. It's a very nice solution as well. And then of course timber fencing, very popular here in Peru. So the reality with paste is that, you know, people may not believe it, but you know, liquefaction is a real risk with paste, and there have been a lot of failures with liquefaction in paste. And the risk is really just for the first 24 hours when you get that initial curing. But you can see some of the incidents, you know, one barricade failed because it had a plugged vent line, and so overpressured the barricade. Been a lot of incidents where they had massive in-stope failures that caused shock waves that went down and blew out the barricades. But the really disturbing ones are ones where if you have water going into the stope at the same time that you have paste going in, and the water and the paste mix, then you end up changing the rheology of that paste, and it basically it can make the paste where it's no longer stable. And there have been a number of failures due to that. And this can happen if you have a lot of groundwater going into a stope while you're pouring, but also if you pump excessive amounts of flush water into the stope, you can do the same thing. So generally we recommend to the clients that you want to be on the plus 2% side of the binder content in order to make sure the paste is non-liquefiable. And then of course with hydraulic fills, it all comes down to the water. Making sure that you don't have water in contact with the barricade by having an adequate drainage system, because if you get the barricades are not designed for full hydrostatic head, and if you get that full hydrostatic head acting on a barricade, it's going to blow the barricade out. And there have been a lot of incidents in Australia over the years where multiple people have been killed due to failures of barricades from overpressuring them. So we always recommend that you have rest times when you're pouring hydraulic fill in order to allow the water to drain out. And with paste, really it comes down again to having that plug pour at the bottom to provide the safety, and then having a continuous pour on top. Making sure that the barricade is set back from the brow of the stove, and make sure that you have a non-entry zone behind that barricade while you're pouring. All right, so that wraps it up. I put that slide in there because the next Mine Fill Conference is in Denver in 2017. And if anybody's interested in mine backfills, that's a really great conference to come to.